All right, so we finished chapter 7, which was taking a look back at kinematics and dynamics just as it applies to rotational motion. So now chapter 8 is also included in this this unit, and it's a really quick chapter. It deals with a couple of a little bit more random concepts. We're going to talk a little bit about equilibrium, which definitely is based upon torque, but we're also going to talk a little bit about elasticity, which is more about stretching and compressing of materials. But that'll be a nice little review of like Hooke's law as we get into this unit. So this unit does start with a pre-lecture video that deals with static equilibrium. So he's going to do a couple demonstrations about forces acting and kind of talking about the difference between static and dynamic equilibrium. But we're going to go ahead and talk about that right away anyway. So section 8.1 is about torque and how it relates to what's known as static equilibrium, a fancy way of saying balance. So static equilibrium we'll take a look at in this section, but essentially it means that something is balanced and it's not rotating and it's not moving. So earlier in the year, when we treated things as just a particle, an object that's at rest was in equilibrium, right? It was static, meaning stationary equilibrium, and the forces acting on it were balanced as well. So as long as the object can be modeled as a particle, static equilibrium is just achieved when the net force on that particle is equal to 0. But now that we understand that things aren't particles, we need to take a better, closer look at that. So now, for extended objects that have the ability to rotate, we need to also consider not just how much force is being applied, but also where that force is being applied. So if you imagine that this object has the ability to rotate and move at its center of mass, in this case, there's two forces, and those forces are balanced. But compared to the bottom one, here we have two torques. And the forces, the magnitude of those torques are still balanced, but if I were to pull on this object like this, there would be some perpendicular force causing it to rotate. So the net force is 0, but the net torque is not 0. So the box won't be moving left or right, but it will be rotating. So for that, then we need to extend our definition of static equilibrium. Before, like I said, it was just a particle, so it's just no net force. But now, it's also no net torque. So the net force on the object must be 0, and the net torque on the object must also be 0 in order for it to be considered in static equilibrium. So a quick check here, which object's in static equilibrium? Well, it can't be A because the forces are balanced. B is a possibility. C, the forces are balanced, but the torques are not. And D and B look, B over here and D over here look very similar. However, there is a larger net force then going to the right with that box. So D has to be the correct answer. So when we choose a pivot point for an object, what we're going to do is we want to go back to this concept of center of mass. So for any object in static equilibrium, the net torque about the object must be 0, and about every point on that object must be 0. And you can pick any point that you want, but you want it to be easy to calculate torque about that point. So we'll simplify the calculations by just looking at the center of gravity as being the pivot point and the center of masses of each side around that pivot point. So we won't really get into too much quantifying, but if I look at the picture on the right, I have this center of mass right here, and that's where the force is acting, that's where the center of gravity is. But then I have these torques on either side of the center of gravity, and those two torques need to cancel out in order for this to be in static equilibrium. And so B is much closer, so it has to have a much larger torque. versus from A, which is much further away, which will have a much smaller torque. So I can do a couple quick demos in class. There's this concept of the quarter and the meter stick, and this one's actually a little bit trickier, but it has to deal with if I have a table and I place a meter stick on the edge of the table so that it is free to rotate, and a quarter on top of that. As you see that meter stick begin to rotate, because of the increased normal force on the table, it actually rotates faster than free fall acceleration. So it actually rotates faster than the quarter is able to fall. So it's a really interesting concept in dealing with static equilibrium and torque being exerted on it, where that is actually going to rotate this way faster than free fall. This is probably a more simpler concept, is that here on the right we have this hammer, and this hammer is tied off to this string right here, so it's causing a weight force going down, but there's a tension force going back up, and the center of mass of the hammer, let me change colors here, the center of the mass of the hammer is somewhere around here, and this is balanced out because the center of mass is under the table. So as long as the center of mass is inside of this balancing point right here, this hammer will balance, and it'll just stay like this just because of this piece of string. There's also a torque going down right here, or a torque going down right here, causing it to rotate, which causes this part to go up, and then there's the normal force exerted down by the ruler, but which is being balanced out by the weight of the hammer, and then there's a normal force going up over here. And all of these forces, there's a ton of forces going on, there's a ton of torques going on, they all add up to equal 0. There's no net torque and no net force. So there's a good little conceptual example. I used to actually solve this as a problem too, but it's a little bit more complex than we need to know. But here we have a ladder, and it's leaning against a wall at an angle of 60 degrees from the ground. What's the maximum, or I'm sorry, the minimum value that the coefficient of static friction must be to prevent the ladder from slipping? So this is actually a really complex problem, because I have, again, all these forces going on, and the ladder, if you look at the bottom, the ladder wants to kick out to the right when you're standing on it on the actual ladder. So when you're standing on the ladder, you're above the center of gravity especially, you're creating this downwards force because of your weight, which is creating a downward torque. Well, even without you on it, that's still happening. There's still the mass of the ladder, and that's acting as a weight force at the center of gravity, and that causes it to want to rotate. So it pushes down, which causes a normal force pushing up against, or pushing perpendicular to the wall. There's also a normal force pushing perpendicular to the floor, but in order to balance out this x component of the normal force, there has to be a force of static friction. So when you're leaning ladders against a wall, there's you have to be very careful on the angle that you lean them, because if that normal force that's perpendicular to the wall is larger than the maximum force of static friction, then you can actually cause the ladder to rotate, especially when you're on it and adding more mass. And as you climb up the ladder, you increase where that center of gravity is. Once you go beyond the center of gravity point, so if you're climbing on the ladder and you're above this point, you're actually causing an increased torque, causing it to rotate. But anyway, let's take a look at this mathematically, and we'll take a look at it mathematically during class. So that's actually it for your quick little introduction into static equilibrium. Now we're going to apply the concept of balance then as it pertains to static equilibrium, and we'll do that in the next section.